Systems of nonlinear equations arise whenever multiple coupled physical laws interact. For example, two temperatures that each depend on the other, flow and heat transfer linked through a common variable, and so. The Newton-Raphson method extends naturally to systems. At each step, linearize all equations simultaneously through the Jacobian matrix, then solve the resulting linear system. Consider a system f of x equals 0 with n equations and n unknowns. Newton-Raphson linearizes f by taking a first-order Taylor expansion about the current iterate x sub k, dropping terms beyond first order. Setting this linear model to 0 and solving for delta x gives the Newton step. Each Jacobian entry j sub ij is the partial derivative of the ith equation with respect to the jth unknown. Add the step to the current guess and repeat until the residual norm is below tolerance. Like scalar Newton-Raphson, convergence is quadratic near the solution. EES builds and solves the Jacobian internally. You just write the equations. Work the first Newton step by hand for the two-stage turbine. At the initial guess, T1 equals 10, T2 equals 5. The residual vector F0 is minus 10, minus 5, giving a norm of 11.18. The symbolic Jacobian has entries 1 plus T2, T1, T2 and 1 plus T1. Plugging in the guess gives 6, 10, 5, 11 with determinant 16. Kramer's rule then gives delta T1 equals 3.75 and delta T2 equals minus 1.25. So the updated guess is T1 equals 13.75, T2 equals 3.75, matching row 1 of the iteration table exactly. Every later Newton step repeats the same three moves. Evaluate the residual, build the Jacobian, and solve by Kramer's rule. A two-stage turbine couples outlet temperatures T1 and T2 through a shared heat load. Starting at the initial guess, T1 equals 10, T2 equals 5, the residual norm is 11.18. The Jacobian at that point has entries 6, 10, 5, 11 with determinant 16. 3 Newton steps from the initial guess and the residual drops to 0. The exact solution is T1 equals 14 and T2 equals 4 Kelvin. Quadratic convergence is visible in the residual sequence 11, 6.6, 0.090. The plot below traces this path in the T1, T2 plane, converging onto the intersection of the two curves. Instead of letting EES solve the two equations directly, code the Newton-Raphson algorithm explicitly so every iterate stays visible. First, define f1 size and f2 size as EES functions of T1 and T2. The main body builds T1 and T2 as arrays, one element per iterate. Unlike a typical loop that overrides a single variable, every T1 of k and T2 of k stays on screen after the run. The whole history is preserved, ready to plot. A flow heat coupling problem links mass flow temperature T1 and heat transfer area T2 through a linear and a product constraint. Starting at T1 equals 350 and T2 equals 3, the residual norm is large at 188. The first Newton step drives T1 to 307.5 and T2 to 3.88, almost eliminating F1 in one shot because it is linear in T1. The second step completes the convergence. T1 equals 308 and T2 equals 4. Two iterations to exact machine precision zeros. The plot below shows both systems' residual norm collapsing in the same quadratic pattern. The same array-based pattern applies to the flow heat coupling problem. Define F1 sys2 and F2 sys2 as EES functions. Three array elements, T1 of 1, 2, 3, hold every iterate, 350, 30, 7.5, 308. Nothing is overwritten. The full history survives the run for inspection or plotting. The Python version takes the opposite approach from EES. X is a single variable that gets overwritten every iteration. X equals x plus delta x replaces the old value outright. Only a short history list is kept, purely for plotting. Define f and j as lambda functions using numpy arrays, then call Newton underscore system with the initial guess 10, 5. The solver returns t equals 14, 4 and 5 iterations. The same answer EES found by preserving every array element. Nonlinear systems. Week 1.